You should have your science journal out. And I have prompted you to read over the notes so far, and that will catch you up on where we are. Um, and you should also have this heading as a new entry in your science journal. And so yesterday we discussed subduction, but we only talked about subduction of oceanic plate. And it's worth remembering that there's not just oceanic plate on the Earth, that we also have continental crust. And so here's a GIF that shows you what happens when you have oceanic plates subducting underneath the continental crust. And then at some point, if the ocean closes up, the two continents will come together. And this is actually a little bit of a review for you. If you look up your vocabulary word orogeny, you'll remember that we've talked about the process of mountain building. And this is often what forms it. This is different than what happened in the Colorado Rockies. That's an unusual circumstance where the plate rose back up and then pushed up. And we'll probably be talking about that a little bit later. Why some kind of unusual circumstances. But what you're looking at here is what has formed the Himalayas. And you can see right here, here's the Indian landmass. And 71 million years ago was nowhere near Asia. 10 million years ago, they finally collided. And because the continental crust, if you would look up that definition again, you would remember that continental crust is too buoyant. Oops. Too buoyant to sink into the dense mantle. What that means is that when they come together, they collide. And that is, of course, what has formed the world famous Himalayas. And you can see the Tibetan Plateau here is basically where one continental crust chunk has thrust up over the other. And the GIF that shows that really well is the one at the bottom here. It kind of shows the layers of rock. So as they come together, you can see one is actually riding up on top of the other, and you can see this big plateau forming. And here's the front of the Himalayas, right? The highest mountains in the world. And you can again see those. That's kind of what you see right here. And then there's this big doubling up of continental crust behind it. Now, part of the problem that we've come across so far is we've kind of presented two options. Either new crust can be formed at spreading centers where mantle rock rises up in the middle and pushes it away, as you can see in this example right here, or subduction can happen, in which case that's where, because new crust is being created at spreading centers, old crust is being recycled at subduction zones. And then I just introduced this idea of orogeny, mountain building, when continental crust gets gummed up in the works and that just piles up. And that actually does eventually end subduction. And a new subduction zone would have to open up somewhere else on the Earth. But the thing to remember about this is all of this is happening on a sphere. The Earth is a sphere. And so this kind of suggests that there's just a conveyor belt. Crust created, crust destroyed. But that's not really realistic because we have different plates and they're moving at different rates. As you remember, there are some places where like in the mid-Pacific Rise, where the spreading is really, really rapid. There's some places like this, like 3 times as fast as it is in the mid-Atlantic ridge. And so what happens is you have all these plates moving around on this 3D, spherical surface. And so things aren't going to move very smoothly. And so the one thing that we're still missing on all this is the idea of where the adjustments are going to be made. And so I want you to notice these stitches here on the mid-ocean ridges. I don't know if you've noticed, but it's obviously, there are these lines that go perpendicular to the general trend of the mid-ocean ridge. And these are these adjustment zones where neither crust is not necessarily being created, but crust is sliding past each other to adjust to all of this movement on a 3D surface. And you can see that also, I think I just closed that window. These are called transform boundaries. And so here you can see what we call a transform boundary is an adjustment place where two plates are moving past each other. And if you imagine this 3D Earth broken up like an eggshell and all this movement on it, this is the way that plates adjust when there's not spreading or coming together. In other words, what we call convergent or divergence or convergence, and we'll be learning those words eventually. officially. So let's go ahead and define that word. So a transform fault is the boundary between two plates that are sliding past each other. So if you please put that wherever you're keeping your vocabulary at this point. I understand you probably don't have room on your list left anymore. Now, I've been remiss in keeping notes, so let's kind of review what we've discussed. One is that orogeny, or mountain building, occurs when two buoyant continental land masses come together at a subduction zone. And that's i.e. the Himalayas. And then the other thing is that on a sphere like the Earth, adjustments to divergence, moving apart the plates, and convergence, plates coming together, are made at transform boundaries. Now, one of the most famous transform faults in the world is in California. You may have heard of it. It's the San Andreas Fault. And here's the San Andreas Fault. It is a transform boundary where you have the Pacific Plate moving north relative to the North American Plate. And what that means is that San Diego, Los Angeles, and the entire Baja Peninsula eventually, and over millions of years, will eventually move up to be parallel with San Francisco. Here's San Francisco right here. Los Angeles, San Diego are down here. And actually this fault leaves the continental crust at the San Francisco Bay, and that's part of the reason why that place is fraught with other problems, which we'll get to in the next video. So one of the things that's very cool, a classic picture of the San Andreas Fault, is that just like in this picture where we had a set of mountains that were originally lined up and then this transform boundary forms in the middle of it and it offsets the mountains, well, the same thing has happened with human features. Here's an example of a fence that was actually built along this boundary. And as a result of that, the fence has been moved apart. So your final assignment today is going to simply get up your blank map, which you have already drawn your divergent boundaries, which are the mid-ocean ridges, and the convergent boundaries, where there's a lot of the deep ocean trenches in the Earth. Not all of convergent boundaries, because as we know now, there are mountain building areas. So I'll ask you to add those mountain building convergent boundaries where you see two plates coming together, but it's not a deep ocean trench. And then finally, I'd like you to add these transform boundaries. Now notice there's a lot of adjustment transform boundaries in the mid-ocean ridges, and that would probably take you a really long time to draw all of those, and I'm not going to insist on you drawing all of them. But if you would please draw some of the major ones, that would be very helpful for you to recognize that these are the places where plates move past each other. So here again, you can see the San Andreas Fault being a very famous one. And there's a whole bunch of other ones all over the country. Okay, we'll see you tomorrow.